All right. Thank you all for coming for the Building Science Graduate Program session. We have, as you guys hear here, we have some attendees online. And after we finish our presentations, it will be posted on our website, so you can have access as well at a later time. We have a number of serious list of speakers here. After the presentation, it will be open for questions. So if whatever question you have, you can hold it, and then we will answer at the end. My name is Professor Tariku. I'm the Building Science Graduate Program Director. And here today, the speakers, myself and Rodrigo Mora, program head for graduate certificate in Building Energy Modeling, and Maureen Connolly, the Director, Center for Architecture Ecology, and Boli, the Program Coordinator, and Ellen, Program Assistant, and Ali Basahi for as a MSc candidate, a student, one of our MSc students. The agenda will be, first I'll be giving you a highlight of our program, and followed by our research infrastructure that we have here in our program. Boli and Maureen will be talking about the building the building envelope and research infrastructure by Boli, and then the Center for Architecture Ecology, Maureen. And the graduate certificate program will be presented by Rodrigo. And then each of us will give you a highlight of what we are working on or what our research interests are. And then Ali will be presenting a highlight of his research project, his MSc project. And then finally, Ellen will be talking about the admission process. And we'll be open for question and answer at that time. And we'll try to give as much time as possible at the end so that we will be able to answer the questions. As many of you might know, building science is actually an emerging field. It's a combination of fundamental knowledge from mechanical engineering, civil engineering, architectural science, and also material science. So putting together, creating a new discipline that will be advancing building envelope design, construction, and operations. There's no many programs in Canada. There are a couple in the Eastern Canada, but there is no such program as such that can give all details from materials to envelope, whole building to indoor environment. As a discipline, as a program, there is no program like that. At the end, we are aiming to have our graduates to be able to design and operate buildings with a full knowledge of whole aspect of buildings, meaning from the durability, from energy and environment. Our program started in 2011, and the program started in response to the industry demand. As some might know, there were crises in the 1990s, leaky condo crisis. From that point on, the industry get together and they wanted to have a facility on research and education in building science, and BCIT respond to that. And we start working program to have this graduate program. As I said, it's the only program of its kind in Western Canada. There might be universities or institutions that might give building science, but those will be courses, not as a full program in the research. And the program originated from the Building Science Center of Excellence, which is with the three fundamental activity. One is applied research, doing experimental numerical studies, as well as field monitoring. And also this center also provide education support to the master's program, as well as the diploma and degree programs at BCIT. And also provide industry support, contracts kind of projects. And these projects will also be part of the students' research project. The program, as it's BCIT, we emphasize on applied research, applied education. So it's emphasized in engineering approach for practical problem solving. and focus on applied research and providing industry solutions. In most projects, we solicit projects, industry projects, what the problems are for the industry, and then we take them as a project, and those will be part of the MH or MSc project. And supported by a strong foundation of research infrastructure, as Borley and Maureen will discuss and show you. We have state-of-the-art research infrastructure here in our program. Our program is financially supported by INSERC, so we have grants from INSERC for research and support to students, and also Canada Research Chair and CFI, Canada Foundation for Innovation, BC Housing, CMHC, and other like Western Economic Diversification, federal government agencies. All these have supported our program's development. In our program, under the Building Science Graduate Program, we have 3 credentials. The first one is Master of Engineering. Second one is Master of Applied Science in Building Engineering / Building Science / Building Science, because this time we are focusing more on more of the heat and moisture aspects of buildings plus acoustics. We don't have structural program or construction management, and the graduate certificate program. So these are the 3 programs we have, and the graduate certificate program has been introduced recently in 2015, and Rodrigo will be talking about it later. So what's the difference between MSc and MH? I have a slide, next slide, but the main thing is MSc is focused on more research plus the coursework. But in terms of MH, there will be more courseworks. But still there will be a research project, what we call comprehensive research project, a 2-term project. The MSc program is at 24 months full-time, whereas the Master of Engineering is a 16 months full-time program. And the thesis based for MSc, relatively less coursework. For MH, more coursework, and the credit hours are slightly different. So MSc is about 36 credits, and the Master of Engineering about 33 credits. Our courses, the graduate courses, have different a combination of different courses. We start with fundamental in building science or building physics, and then followed by advanced building materials, building envelope design for wall and windows, and building envelope design for roof and foundation, and energy performance of buildings, mechanical systems and control, acoustics, advanced acoustics, and advanced energy simulations. Now we added measurement and verification as well. So as you can see, all these are all applied to buildings, and all it tests all indoor quality and ventilation as well. So it takes care of all aspects of buildings performance. These education activities are tied with our research activity, which are mainly on envelope, energy performance, indoor environment, and acoustics area. And these research areas are also supported with, as I mentioned, with state-of-the-art research infrastructure for all these activities. Now I'll leave to Bo to go through our research infrastructures. Bo.
Good afternoon, everyone. I will give you a brief introduction about our research infrastructures. As can be seen here, our program has advanced facilities and equipment that enable the experiments under controlled indoor and real outdoor climatic environment conditions. Those research facilities include the hydrothermal property measurement lab, the building envelope test facility, and the whole building performance research lab. Those research facilities and infrastructure with our program are all accessible to all students. The hygrothermal property measurement lab is equipped with the test apparatus to measure hygrothermal properties of commonly used construction materials, including the material density, vapor permeability, isothermal absorption, water intake, and thermal conductivity, and also the air permeability. As can be seen here in this picture, this is the building envelope test facility. This is a very unique research development and demonstration resource. It is created to evaluate the hygrothermal performance of full-scale building envelope assemblies and the associated products under simulated indoor and real climatic outdoor conditions. The total floor area of this test center is measured by 44 by 28 feet. It's quite big. And it's only known two-story facilities of this kind of research facility located in the western coastal rainforest for environment. As designed as a multiple purpose testing and training center, this facility has the research capacities to, for example, advance the knowledge in quantifying the wind-driven rain, to evaluate and develop effective rain control strategies, to evaluate the long-term hygrothermal performance of some innovative envelope systems and building materials, and to investigate the impacts of the building envelopes on indoor environment. This picture shows this is the whole building performance research lab. It is a real-time, real-weather exposure facility used to conduct research on a dynamic interaction between building envelope components, the indoor environment, and mechanical systems. This lab has two, as can be seen, has two identical 250 square feet buildings that are fully exposed to real outdoor environment conditions. One of the buildings is used as a reference, while the other is used as a testing building during the evaluation of alternative design options. This lab can evaluate various building design options in a holistic way with the objective choosing design parameters that can lead to a reduction in energy consumption while maintaining the indoor humidity at an acceptable level for occupants' comfort and health, and the durability of the building envelope components. A variety of computers building performance simulation tools are available in our program for students to learn and use. A selected list of those simulation tools are shown in this slide. Except for those commercially available computer modeling tools, we also develop several in-house simulation models. For example, the HAMFIT and HAMFIT Plus to explore the hygrothermal performance of building envelopes and whole building performance. And this is a full-scale environment facility, and we call this environment chamber, which is currently being assembled. The environment chamber is a multi-purpose testing facility which is able to investigate and evaluate the performance of the full-scale building envelope systems, such as wall, a whole bunch of one piece of the wall, or a window systems of the building under controlled environment conditions. And I will pass this to Maureen.
Thanks, Bo. Good afternoon. The Center for Architectural Ecology was actually founded in 2002, and it serves the whole of BCIT quite broadly. The School of Construction, the environment probably gets the best share of it. And within that, my attention to the graduate students within the building science program, well, they get the best share of me. So I'll just go through a few slides. This building is actually about 200 meters or so away from Alan's office and Fitzsim's office, but it is not in the large building, any one where you go to typically meet with the faculty. Just a little way to the east. In there we have a living architecture lab, and that's where I work on green roofs, living walls, or green facades, or rainwater harvesting, or water flow as it may affect the building envelope and the acoustical environment. There's also two other images in here. One is in the same area, the building envelope transmission loss setup, And I will speak to that a little later when we talk about research, a pretty exciting project coming out of there. And then we have a 1 to 10 scaled anechoic chamber. So that anechoic chamber is like being in the middle of outer space. So no sound is reflected back. Boeing, for instance, has one that's so big they can put their super jets in it. And that's how we can understand the radiating intensity of sound. So we do everything at 1/10 scale, just like you would an architectural model, and we take the sound waves and bring them down as well. Across from the Building Science Center and our center, we have an elevated lab, and that's very supportive in that it's a very large rooftop space where we can look at outdoor sound propagation, and we can also play with different aspects of living architecture. And we have data acquisition and weather station there 24/7. Across Willenden Street, we have a sound suite, and that sound suite facilitates sound transmission through roof systems, so we can take roofs on and off and look again at the radiating sound energy. And the inside of the sound suite acts as a reverberation chamber. And from there, we can study characteristics of all the different building materials in terms of their absorption of sound energy or their scattering effects of energy, which is pretty critical for inputs into prediction modeling. I mean, that's a fun one there. Some inventors came up with a light, and it's made of Tyvek with the little LEDs, and they said, we installed these, and it makes the space sound different. And we're saying LEDs and Tyvek? And sure enough, we actually were able to establish that it had some potential to correct speech intelligibility in rooms. So there you go. The students hang out, for the most part, in the acoustics lab. And in the acoustics lab is where we keep most of our equipment. So we have real-time analyzers. We just received a tapping machine. We've got a great project that has gone out and been published on the different types of roof decks and green roofs as well, and how they affect space below that. Omnidirectional speakers and regular speakers. Sound books, intensity probe. This is one of these things that there's only one in Western Canada. Well, there's actually two in Western Canada, so it's a pretty nifty piece of equipment. And then we use a fair amount of softwares, whether it be those that we've calibrated ourselves or we've purchased off the shelf. The biggest one there being Odeon, and we actually work with them as well for the development of software and calibration of that. So that's the infrastructure we're using. And it's also how it vends with the other departments. Cheers.
Thank you, Maureen. Okay, currently our program has about 43 students in total. So 21 of them are Masters of Applied Science degree students, and 20 of them are working toward their Masters of Engineering degree. Another 2 students are pursuing their graduate certificate of energy modeling, which is our new program. Those students enrolled by our program come with a variety of engineering and architectural design background, including architectural design, civil engineering, mechanical engineering, electrical engineering, materials, integrated engineering, and other engineering-related fields. So far, we have 42 graduates from 18 countries finished their study and graduated from our program. 34 of them achieved their Masters of Engineering degree, and 6 of them achieved their Master of Applied Science degree. Another 2 obtained a graduate certificate in building energy modeling. Among them, around 30% are female students. Okay. Career opportunities. Career opportunities for our graduates are available in the construction industry, including building envelope consulting, acoustic consulting, mechanical engineering, and architectural consulting firms, and also university and colleges and research institute, government. So this slide just to show the companies which our graduates are hired and currently working for after they graduated.
Thank you, Paul. Hello, everyone. Okay, so I'm going to talk about the graduate certificate in building energy modeling. It's a new, like it says here, new graduate certificate. And you may wonder why new, why energy, why modeling? Well, new because there's like all the other programs in BCIT, and especially in our program building science, it comes from a need from the industry. So the industry required and approached BCIT to develop the certificate. Because there's a growing demand, as you can imagine. What is energy? Everything we do consumes energy, and our buildings are big, huge energy consumers. And energy consumes resources, and resources produce CO2 and so on. So energy is becoming a huge target, and it's a central area of building science. So you can see it as a specialization of building science, building energy modeling. So again, it was driven by the industry, and you can see now, for example, there's the new codes for those of you that are aware that are coming, the City of Vancouver BC Building Code, that are being more and more stringent in energy efficiency. And you know we're going towards net zero energy. So we need support to achieve these targets. We have net zero energy targets, and then how do we support that? Well, there's energy modeling. I call it a true green discipline. True is a green job, and this is a sample of green job. So yeah, this is building energy modeling. So what is the modeling part? The modeling, why modeling? You may think modeling is this computer thing, computer crunching. Well, building energy modeling is, you can see, it's a tool, it's a powerful tool for decision making. So it helps us make decisions about how to reach these net zero energy targets. So that's why. But the thing is, we're not really focusing on, I think I'm going ahead of myself. In the next slides, I'm going to talk a little bit more about that. So what else is here? It's a one-year fast track program. So it is not, it's shorter than the other programs, shorter than the other two programs, and it's very focused on energy. So that's the message here. It's an emerging discipline, supports capital decision, and supports the integration. So you all these things, but the most important thing is, energy modeling, people think, is a tool. It is a tool, but here we emphasize not on the tool itself, but on the physical principles behind that. So we try to go to the like what Fitzum was talking about here and moisture transport, about what's going on in spaces, the mechanical systems, how they operate, and so on, is not about using a modeling tool. So by the way, this is why the industry approached BCIT, because they saw our program in building science, that it was very much principles based. And they like that, and they say, we want energy modeling to be based on principles, not on number crunching. So you see here are examples of the kind of decisions that are supported by building energy modeling. I'm not going to read through all this, but you can see here, and I would say it's the most powerful tool nowadays to support decisions in buildings. So here you see the program map, and you see there's three streams: the building science stream, the building energy stream, and the management and communication skills stream. And this stream is new. It's something that was, again, the industry came to us and said, we need engineers that are good, really technical people, or architects or professionals, but they know how to communicate what their results. And then you interpret your models, and they need good communication skills and management skills. So this is new. This is part of this is not in the other programs. And then for this certificate, we developed new courses. For example, the measurement and verification course is new, was developed. And these are core courses. All of these are core courses in the certificate. In the master's degree programs, some of these are elective, but here all these are core courses. Like I said, it's fast track 1 year, but it can be taken part-time, because we understand that people work in the industry, and then they cannot afford taking it fast track. Okay, so that's about the certificate, 22 credits. And I think I'm going to move on to the research. So, okay, so I'll start talking about my research. So these are my interests, as you can see there: indoor environmental science, indoor environmental systems, and systems integration. As you can say, these are the main areas. So what is environmental science? Is what's going on in here in the spaces, about the physics, the air movement, it's not just about physics, it's about physics is the central part, but about how people, it has psychology part too. You know, some people feel warmer than others, some feel colder, and there's some psychology involved in that. Physiology too. So we collaborate. This is not multidisciplinary, so we collaborate with people from different disciplines. So it's very interesting. For example, the air thermal comfort, indoor air quality. What is it? The building science, the environmental science about air quality, where we need to understand contaminant emissions, transport in buildings, how contaminants move to maintain buildings healthy, where they are produced, from what activities. So that's indoor environment and systems, because we need to know how to deliver this indoor environmental quality, you can say. So we need, so the systems, when we talk about systems, I'm not just talking about the mechanical, but envelope, all the different systems. So that's why I think I try to see this more as an integrated view of indoor environmental quality. So here are some samples of what I'm working on right now with students. Human and environment centered building engineering. So what is that? I mean, because we're slowly recognizing, you can see this future image in the future, is that we're kind of very reliant on mechanical systems. We put heavy emphasis on the mechanical systems, and it should be the other way around. There should be more emphasis on the architecture and the passive design, and then minimize the mechanical systems. So that's the goal. That's kind of the core kind of philosophy, you can say, behind what I'm doing. And here you see an example of a paper with two of our students. This is James here in this paper, and he's monitoring, he's logging actually the data from this operation of the door. Because of course, people open doors, open windows, people do things and affect the performance of buildings. So the idea of this is to see how occupants and buildings interact. In the past, the paradigm was occupants were passive receivers of the buildings, and we receive whatever the building gives you. Well, we realized we have to make buildings more responsive to occupants and to the environment. So that's the idea. So anyways, these are areas: intelligent sensing and control, occupant awareness, responsive systems. So that's the goal, to develop more responsive systems to humans and to the environment. And then in the end, as a side effect, you can say you save energy. Another project or projects that I'm involved in is building data analytics. That's a very interesting area, because that's, again, you will learn from the building. The building automation systems provide lots of data that can be supplemented. We can put our sensors, and we're in fact putting sensors in buildings, but we have a lot of data coming from buildings already, so we can use it. And here in this figure in the top, the colorful one, I like colors, you can see that the darker ones mean some rooms are overheating over a period of time. And this is from the data from the actual building. So we have to do, and the one on the bottom, you cannot read it, but it shows the systems, the heating systems. It's a radiant floor heating system. So we try to correlate the two. Why is it overheating happening? And develop some analytics rules, basically, to find that. So that's an interesting project we're involved in. And the other one is kind of the paralleling housing, healthy housing. You can make the analogy to the commercial buildings, where we have remote sensing. So we have in a couple of houses, and we're trying to instrument more and more houses here in Vancouver. This is a very, very green house, green home in Vancouver, developed by the code, the newest code that is triple glazing and so on. And then we're monitoring. So we instrumented the house. You see the data logger there. We instrumented the house with some students, and then we're monitoring the house, and we can see the data from the cloud. And we're going to use some analytics again to study the performance. And we're giving questionnaires, because again, this is about psychology too, to people, how they operate, how they feel in the house, and so on. Okay, so let's pass it to Fitzu.
Thank you, Rodrigo. All right. My research interests, one is in innovative materials. So innovative materials, right now, as we know, the code has been changing every time. There is a big push in having high efficient buildings. To achieve that, one of the things that we have to do is on the envelope, meaning to have high performance envelope systems. To do that, one of the materials that we need is the insulation material. with the current materials, we may not be able to achieve what we wanted to achieve. So one of my research areas on material like aerogel insulation material, vacuum insulated panel, natural-based fiber reinforced insulation material, and also combination of different insulation materials to be able to achieve high performance of envelope systems. The next one is on a building envelope design. So one is in the first one, I'll be looking at a material level using the facilities that Bo was talking about earlier, looking at each material's property, both from the thermal and hydrothermal property perspective. And then moving to the building envelope, now knowing each material property, we can put it together and see how it performs as an assembly or as a whole system in the building. So this is done through experimental and modeling activities. Right now, we are working on, and my students are working on innovative, high-performance, next-generation building envelope systems, R40, R50 wall systems. Not only looking at from the energy aspect, but also looking at from the moisture or durability aspect of the system. So if they are not durable, there will not be no use. In the building envelope design, we're also looking at like what Ali is going to be talking about as well on details and thermal bridges. We know significant heat loss will be, or the weak element of a building is at connections or thermal bridging areas. We are trying to develop designs to reduce thermal bridging effect of envelope design, and also to develop tools to how to account the thermal bridging, two-dimensional, three-dimensional thermal bridging effect in numerical simulations. Right now, we will have just a one-dimensional analysis. Right, another student is trying to develop a numerical model to do two-dimensional, three-dimensional representation of details, so that we will be able to simulate in a real way of building simulations. I also work in energy performance analysis and optimization for cost, energy performance, and life cycle assessment, and thermal comfort. So we will have a building. It has to be optimized at least for costs and also these important parameters. So we are working on developing models and tools, combination of different tools, MATLAB and Energy Plus and so on. Try to develop optimization tools. We are also looking at building integrated photovoltaic and thermal systems. How could we integrate these renewable energy systems to buildings, and how could we actually, in addition to, for example, in PV panel, in addition to electricity generations, how could we tap in the energy, the waste energy from the PV panels and use it for integrate with the mechanical system for heating? So we are working on that, both on the experimental and numerical modeling in that aspect as well. And the last one is life cycle assessment. So as I mentioned, I'll be focusing first on new materials, using those facilities, all those properties from both for the thermal and moisture will be characterized, and it will be assembled. And then now you'll have envelope, and we can look at the whole the envelope performance. Now we integrate it into the whole building. Now we can have occupant simulators, people behaving how they, in terms of their thermal and moisture generations. And then we can look at the whole building performance as it's exposed to real outdoor climatic conditions. And then finally, we'll have numerical methods to assess the energy performance, the durability, as well as the long-term performance of the system as in a whole. So this is my research is whole building performance integration of envelope, energy, and indoor especially thermal comfort and most humidity control. I do lab and field experimental studies as well as computer models, using existing computer models and developing new models. And the inputs are material property, which can be characterized from the facilities that Bo showed. And we have a weather station for climate. So that will be the input to the model. And then from the lab and field experimental study, it will be the models will be validated. And then the validated model used for design of experiment. And then once this cycle is completed, the model will be used to predict how to perform in other kind of scenarios. So this is an integrated approach that I'm undertaking at this time. And a number of students are working in a different area of this map. I'll be to the next one, to Maureen. Thank you.
Well, I like that last slide because I could adopt that one, and I think we all could, and it's great. So I have a different approach of how I was going to explain to you my research work. I thought I would go over some of my students' projects, those that have graduated or those that are working, because as each one of us, we have fairly large fields of endeavors, and so you might be sitting out there going, well, you know, what piece might I get to do? So that's how I'm going to approach it. But I can summarize it. First, it's in architectural acoustics. And when we talk about architectural acoustics, we're talking about the larger community, so outdoor sound propagation. One of the things that's very much happening here is an increase in densification of this city. And as you increase in densification, you increase your noise level, your ambient noise level. And we have to deal with it now. And it's just starting to happen here on the West Coast. So there are people in England, people in some of the developing countries that are well ahead of us in terms of their densification and noise source. The need for that research obviously is tied to the issue of health, where noise can create stress and cardiovascular disease and cognitive delay and a number of other health issues. Those would be epidemiologists that I collaborate with that work on that. So architectural acoustics, it's what's happening in the exterior environment. The next part is we follow the path of where that noise goes. And for us in the building science area, it's going through the building envelope. So there's a fair amount of research around sound transmission through the building envelope. We'll cover that in a bit. And then what happens inside the building. And that ties into the whole concept of indoor environmental quality, where acoustics is very much part of that. In terms of living architecture, the focus there is on vegetated roofs and walls. And the reason they come together for me is because I had those two aspects of my research. I did extensive amounts of research on living architecture in the area of energy, and there was the area of stormwater mitigation, habitat, maintenance, plant species, and communities. And then I said, no, I'm not going to go there anymore. I'm just going to let it vend with my acoustics work. So I have developed that expertise in the acoustics of living architecture, and I quite enjoy advancing that topic. The reason I have soundscapes up there, it's up there as a simple word. For some people now it's become a new buzzword. But really what we're talking about, well, let's take what's happening in this room, in this space here. There could be sound coming through this envelope. There's certainly sound that's coming from the diffusers, the mechanical. I'm making sound. Some of the equipment's making sound. So you have a whole pile of sources and a whole pile of receivers in the room. And that's an ecological model. So that's quite different from a very mechanistic approach, you know, Ashgrave, chapter 48. Here's a heat pump. I mean, we do this in the course. Here's a heat pump. Here's the path. Here's the diffuser, here's the receiver, the person sitting in the room. And we do look at noise criteria, but that's very mechanistic. And it's only one path. So how does that tie in with the comfort of using the space? A lot of the research which Rodrigo's doing. So that's more an ecological approach, or we'll call it soundscape. And this photo is a bit of a joke. It's a new photo BCIT just took, and it's going to be on the supply trucks that are delivering goods all over BCIT. It's one of my students in our lab. But what's real about this photo is those supply trucks actually delivered these living walls all around BCIT and out at UBC for our data collection. So I said, okay, you can have the picture on the side of distribution trucks. So I'm just going to give you a few snapshots of the students' work. The first one is also a success story of the student. Rosalind, actually, she was our first graduate out of the program for the Masters of Applied Science. She was then with me as a research analyst, and now has headed off to ARAP in Chicago as an acoustical consultant. And our work together was really fun. We were looking at this issue of laneway housing. So laneway housing is a new type of densified community, but more intriguing, well, equally intriguing, is the fact that we're moving transportation noise down a canyon. So we have to all of a sudden look at outdoor sound propagation and noise buildup. So it's a new type of source, a new way to analyze a source. Like who would look at a laneway in that manner? We're also looking at small volume housing and new materials, and how does that impact the sound transmission and the resulting sound level in the laneway houses. So that was a fun one. In terms of mechanical systems noise propagating across the community, we're starting to inhabit rooftops. We want to have healing gardens up there if it's next to a hospice or as part of a hospital. Certainly downtown, we have all these daycares now that are up on top of roofs. And at the very least, we want to have like real cool cafes on top of roofs so we can have a great view. And all of a sudden, we've got this chiller blasting out 85 dBs. So we start to look at, could green roofs in effect act as a sound source? So that was another student piece of work. Scattering coefficients gets very technical, but that is when we start to look at how we can actually examine different materials and whether we used a material such as mosaic, a material as a model diffuse board, or even plants to scatter sound energy. Very critical for prediction models. This set of 3 projects actually describes a little way as how I like to work with students. It was 3 different graduates, 3 different students, all taking their Masters of Applied Science, one of them at UBC, and a co-supervisor, a microbiologist from UBC. So we created 3 student projects, funded through CREATE. So the first student really investigate living walls and the architectural or acoustical characteristics of the walls relative to the plants, to the soils, to the mechanisms of the porosity of the different substrates and water moisture content, relative humidity. And she understood the systems and the variety. A second student looked at these same living walls, and that's Ivan down here, and he's looking at air quality, VOCs, endotoxins, CO2s, bacteria. And all that had to be the microbiologist, not the acoustical person. So that was my colleague, Karen Bartlett. So we have these 2 students that developed this understanding of these living walls, and now we have the third student who is taking that data and developing prediction modeling tools. So that's one of the reasons we have to move our infrastructure around sometimes. So this was a very, this is over 4 years and 3 students, plus little bits of extra students, maybe undergrads as well, supporting it. But we develop a whole project like that. Now this one, this is fascinating for me. When I started lecturing in acoustics back in early 2000, in the middle of that leaky condo crisis that Fitzum talked about, I said, guys, don't worry. Once these buildings stop leaking, everyone's going to be a little upset about what they're hearing. Like when people stop paying $300,000 for their apartment and start paying $3 million for their apartment, they don't want to hear the toilets flush. They don't want to hear water dripping off of the top flashing, the head flashing. So this brings me to 2 specific projects. One is about water and how it can actually provide masking. That was one. The other water projects that we've used have been waters through downspouts. That was one little project that was done by an MEng student. We're really having problems right now with some of the building envelope retrofits where the head flashings deliver the water directly to the sill flashing. So we're starting to analyze this whole issue of water diversion off the new building envelopes. And it's coming quite nicely together as a collective research package. The other piece that came out of that leaky condo crisis was, there are new building envelopes mandated through BC Housing and Code, and they deal with heating, air, moisture, and everything that my colleagues here will speak about. But one of the things that happened is they developed these without an understanding of the acoustical impact. So we had 2 big projects come out of this, and we're in the midst of them now. One of them is if we're going to ventilate a rain screen as a building envelope, we're bringing air through that system. We're bringing noise through that system. Are we making spaces in that new rain screen where we have mass-to-air mass resonance? Are we venting systems that are actually going to cause more problems in a particularly loud environment, like with high transportation noise levels? So we're doing that little piece of research. It's not a little piece. We really needed to understand, when they were testing them at the National Research Council as face sealed, but we have as a minimum a drainage gap Or maybe we have two gaps for a completely ventilated system. What is the impact on how we test? And now, what is the associated sound transmission of these new systems? So we've just evaluated 50 systems. Now we'll head up to Ottawa to do some big testing at their facilities. And then, oh, so yeah, that's one student up here who's also now with me as a research analyst, using the intensity probe to analyze these systems. A new directed studies. I thought I'd throw this in as a directed studies project. Mostly we're talking about full thesis or full MEng projects, but as a directed studies project, we have one where we're looking at the symbiotic relationship between photovoltaics and green roofs. So in a cooler environment, the photovoltaics works better. With a little bit of shading, you actually can have more biodiversity in green roofs. And then lastly, I think everyone here in our department, in case I don't get a chance to say it, we have a lot of fun. Here we are, a group of the international students. I think you showed 16 or 18 countries that everyone comes from. So we went up snowshoeing. We hooked off, sorry Fitzum. We hooked off one Friday afternoon. We went snowshoeing and had a lot of fun. So I thought I'd leave you with that one. And now it's back to Bo.
Thank you, Maureen. And I guess I need to just spend 1 minute to introduce myself a little bit, because before I joined BCIT, I spent many years in industrial field. I was a high-rise building mechanical system designer and a energy modeler, building performance analyst for many years. I also got some practical work experience in terms of the plant operation, some hands-on experience in terms of fixing mechanical systems. So that's why my research mainly is focusing on the building performance simulation, first of all. So and also I'm very interested in investigating the impacts of different types of mechanical systems or ventilation systems on the whole building performance. And then also building has lots of wastage. I don't know if you're aware of that. For example, when we exhaust air in a winter time, and it is warm air, basically you exhaust. Even though the air is contaminated, you don't want it anymore, but energy associated to this amount of air has been released to outside without being reused. And also the sewage. I don't know if you're aware of the sewage water. When you drain that, the temperature is still higher relatively. When taking a shower in the morning, when you drain that, if you measure temperature of the water drained through your bathtub, it is high temperature. We're able to harvest those waste energy and reuse them, so that make building perform even better, more efficiently. This is my research interest. However, I know lots of people, and also many of the research jobs have been done in terms of harvesting, wasting energy from a building. However, many people might have a wrong concept in terms of using, for example, heat recovery unit. Everybody thinks heat recovery unit is kind of like a magic unit, and you install that, you blindly use them, and you will save energy forever. But after you're using it for a couple of years, you're checking your utility your bills, especially in Vancouver, maybe you don't save that much, and we need to find out why, right? And so, of course, the first step is we're trying to build a numerical simulation and for a real house or building, and to simulate that. Once the model has been built, and then we want to calibrate the model. So we make sure the model actually is telling the right things to us. So through the model, and we call this model archetype model or something like that. And once we calibrate this model, and we can run the parametric, we can conduct a parametric study. So we can actually simulate the building with the HRV systems in different climate zones. So and the other thing is, if you look at a mechanical systems, we talk about different types of mechanical systems. In this room, I'm not quite sure, maybe the VAV systems we're using, and we might have 4-pipe fan coil systems, and we could have let me see, in the house you could have the simplest one, which is the hot water baseboard heat, or electrical baseboard heat. Or some house maybe can be equipped with a floor radiant heating system. All those different types of mechanical systems, when they perform, when they operate, what is the energy consumption in comparison in different mechanical systems. Some people might spend lots of money, invest lots of money to build a soup, we call it green building systems. However, when you check the actual energy saved by using this type of energy mechanical systems, they might be very minor. And then also from the owner point of view, it's very, very reasonable to run a life cycle cost analysis. For example, I invest an additional $500,000 to build such a fancy house with a very high efficient mechanical system, whether or not compared to the baseline building, I'm actually saving something, and also my investment will get a reasonable payback here. Although things are of my interest, I'm doing this. Currently, I'm planning to conduct a research on a real house, which is supposed to be designed to have to perform in a more energy efficient way, and that building use a geothermal systems. So I'm gonna first, I will go to the building. If I need to fix some of the mechanical systems in terms of measuring instrument, I will do that. And then after that, we will build building a numerical simulation model. We are going to use transits, and possibly we would use some the MATLAB Simulink, because as you know, not all the energy modeling tools are designed to model or explicitly model all the mechanical systems, because sometimes the mechanical system designers are very innovative, and it's crazy sometimes, we call that, and they design systems which is very interesting, cannot be explicitly or directly modeled by the numerical simulation tool. So what my job is trying to find a good way to model that, and if it is necessary, we will do some coding. And after that, we tune the model, and then we run the parametric run and investigate the impacts of the different mechanical systems and the control strategies on the building performance. And hopefully for the same building, but in different climate zones in Canada. Okay. Thank you.
Good evening, everyone. My name is Ali Wasegi. I'm a Master of Applied Science candidate under supervision of Dr. Fitzon Perico. I have a few minutes to briefly go over my research thesis, and then I talk a little bit about BCIT Building Science Student Club. The topic of my thesis is analysis of alternative building envelope designs to improve the thermal performance of concrete buildings. Buildings consume a significant amount of energy for space, heating, and cooling. Well, about 40% of total energy use is consumed for building sectors. Right now, transmission heat loss through building envelope components constitute a major portion of space thermal load. Additional heat loss in multidimensional assemblies of building envelope, such as corner wall, balconies, slab edges, and parapets, has negative impacts on moisture growing occupants' thermal comfort, moisture condensation, and energy consumption of buildings and also their occupants. Therefore, it's essential to design building envelope details in a way that reduce these negative impacts on buildings and their occupants as well. My research is about minimizing heat loss, minimizing heat loss in concrete buildings by developing high thermal performance building envelope systems to exceed construction requirements of local codes and energy codes, and also standards such as ASHRAE and LEED. Activities in building science program are not limited to research and studies. We also have a community for students to get involved more. The Building Science Student Club, or BSSC, is an organization that is started and run by students for students. Our goal is to help in creating community to support new students, prospective students, and current students as well. Events of the clubs include academic seminars, site visits, and social events. Well, all in one, I just want to say I'm happy that I found this program. There are lots of demands out there for students who graduate from this program. I encourage you to go for this program. You'll have my support for sure.
Hi everyone, I'm Ellen Scobie. I'm the graduate program assistant. So if you phone or if you email, I'm going to be answering your questions, so feel free to contact me anytime. All our entry requirements are on the website, so I'm not going to go over all of that. I'm just going to highlight some of the most frequently asked questions that we get. So to reiterate, the deadline is May 31st, and that's for everybody, resident and international students. If there are seats available after this deadline, we do keep it open for a second round. Applications will be received until July 15th, only for resident students. International students must have their applications in by May 31st. The application process is completely online, so please have a look at the website and follow the directions there. I've got the link up there for you. GPA is an important part, not the only part, but an important part of your application. You need a minimum of 70%. That's 2.8 out of 4. We get lots of questions from students whose GPA might be a little bit low. What can they do? We do give you the opportunity to boost your GPA. And you can do that by reviewing your transcript and looking at those courses that you scored poorly on and then repeating them. You obviously don't have to go back to your original institution. You can find that course at any post-secondary. If this is something that you feel that you need to do, please contact the department and we will approve the courses that you see as your repeat courses to make sure you're on the right track for that. This is how you calculate your GPA. You multiply the number of credits in the course by the grade to get the product grade point. Then divide in your total course credits into the total grade points to get your CGPA. Students with an architectural background typically don't have the math requirements. They're not typically part of architectural programs. If you are coming from an engineering program, it's most likely you already have this math. So we're not asking you to do it again. We just need you to highlight for us the courses that you took. If, for instance, you took a linear algebra course and on your transcript it says Math 2 or something like that, please supply us with a course description so we can verify the content. In order to get an idea of what we're looking for in terms of the content, we've provided 2 references to UBC courses. The linear algebra should be equivalent to the course description of UBC Math 221, and differential equations equivalent to UBC Math 255. BC Transfer Guide has an online resource where you can go in, plug in the UBC Math course, and it'll give you all the institutions across the province that offer a similar course, an equivalent course. So you can take it anywhere, and there's online options as well. So if you need those, please contact me and I'll give you the link. Thompson Rivers University and Athabasca both offer online courses for the math. If your undergraduate degree is from an international institution outside of Canada, also outside of the US, the UK, Australia, or New Zealand, you will be required to get a comprehensive report from the ICES the International Credential Evaluation Service. And we need that in order to qualify your undergraduate degree in terms of Canadian education. So that is a mandatory part of the application. If it's getting towards the end of the deadline, May 31st, and you've got everything ready, but you still don't have your ICES report, please still do apply. Send us your original transcript, and then if you are accepted, it'll be pending the receipt of the ICES. But don't let that hold you back from making the application deadline. A qualifying student is a special designation that we give to MASC students who have been accepted by a supervisor but have perhaps not yet met the program requirements. For example, they don't have their math, or for whatever other reason. But they've been in contact with the supervisor and they've made an arrangement for the student to come on. So you won't have an official BCIT status, but in terms of the department, you will be saved a seat for the next year. We call that qualifying student, and that is a designation to allow you to prepare your academics prior to acceptance. There are opportunities for assistantships. These are mostly for MASC students, and the money is available directly from the supervisor. So if it's something you're interested in, please ask your research supervisor about it. There is limited funding available for MEng students. NSERC, the Natural Sciences and Engineering Research Council of Canada, has a Canada Graduate Scholarship that is applicable to our program. That's well worth looking into. We also have funding available through industry and the BC Building Envelope Council Award. Our program also offers the opportunity for professionals to take 2 courses without applying to the program. So if you're interested in professional development, you're interested in the building science field, you're not ready to enroll in the master's, or it's not something that fits with your plans, if you meet the program requirements, you may take no more than 2 courses. If that's what you're interested in, please just send an email with the name of the course you'd like to take, your resume, and your transcript for department review. That's my contact information, so feel free to contact me if you have any more questions. Right. That concludes our presentation. Thank you very much for coming, and we're open for questions.